We're very happy to have Howard Haber here for the last talk of the semester. Right? Then so Howie is professor at UC Santa Cruz, talking about some banana slugs. He's going to show us some cool other things besides banana slugs, like these RG stable parameters without any symmetries. So without further ado,
All right, well,
take it away.
thank you for the invitation. It's always fun to come and visit NYU. And what I'll talk about is based on this paper, which will show up in the journal as soon as the editors could get the proofs correct. It's unbelievable how many rounds you have to go with these guys before they do it right.
We're recording this.
Oh, okay. So the outline of the talk, I'll start with what I like to call a folk theorem, at least something that I believed in, and a lot of my friends believed in, and it seems to not be quite true as stated. You think you know basic things about quantum field theory, and one day you're very surprised. And this whole story, there's a story behind this, and it has to do with some folks studying the 2x doublet model. And the 2x doublet model is an extension of the standard model. You add a second complex doublet, and suddenly you have lots of new parameters. So for instance, the scalar potential, after you solve for the minimum, you have 11 parameters. That's a lot of parameters to deal with if you want to tell your experimental friends how to find these things. And so what people tend to like to do is reduce the number of parameters by imposing symmetries and have something a little bit easier to deal with. In the early 2000s, there was an attempt to classify all possible symmetries of the 2 Higgs doublet model that you could imagine. And then people studied the phenomenology of the various kinds of 2 Higgs doublet models that you got out. Now, the big surprise about 2 years ago now was a couple of folks were examining some special cases of the 2 Higgs doublet model, and they discovered a parameter relation which didn't seem to come from any of these symmetries that had been classified. So the big question was, had they inadvertently discovered a new symmetry that the previous classifiers had missed, or what was going on? And it turned out that it wasn't missed, and this actually looked like a parameter relation that was not being enforced by any known symmetry. And moreover, these parameter relations were normalization group stable, not only 1 loop, but 2 loops, 3 loops, and they're able to show that, in fact, to all orders in perturbation theory, at least neglecting the Yukawa couplings, these parameter relations are totally stable.
Neglecting which couplings?
Sorry?
You said neglecting certain, I couldn't hear which.
Oh, Yukawa couplings.
Yukawa, okay.
Now, they included the Yukawa couplings. They're able to show up to 2 loops. They weren't able to prove an all order statement for the Yukawa couplings, although they suspect.
There's no, it's not known to not be true.
Yeah, you're right, exactly. And so this sparked my interest, and to try to really understand what was going on here, it turned out that there was a very nice toy model, much simpler than the 2 Higgs doublet model, that had all the same features. And so we could sort of handle it in some sense and try to understand what was going on. And our solution to the puzzle will have to do with this concept that we call complexification. I'll explain that later, and symmetries of a complexified version of this theory here. And I'll try to show why that leads to the RG stable parameter relations of the original theory where the symmetries weren't present. Okay, so in quantum field theory, there could be a lot of parameters, and if you just by hand say, I want this parameter equal to that parameter or some other parameter relations, you know that that's in general going to be a statement that is not preserved at all scales. And it might be and therefore setting that parameter relation is considered a fine tuning. However, if there's a symmetry reason underlying that particular parameter relation, then that parameter relation is stable to all orders in perturbation theory, and it's also, it continues to be stable if the symmetry is softly broken, if we're talking about, say, tree level relations satisfied by dimensionless couplings. Although you will get finite radiative corrections, but at least they can be small. So the question is the converse of these above statements true? And the folk theorem that a lot of us believe was that if you ever encountered an RG stable parameter relation, there must be some symmetry lurking behind that gives you an understanding of where this comes from. And this was the paper that sort of shattered that belief. Here's the reference down here. And once these authors wrote down this version of the 2x doublet model, and it didn't seem to have any symmetry origin, they attempted to resurrect the folk theorem by inventing some sort of bizarre symmetry. And of course, the question was, is what they came up with, is it a legitimate symmetry? Is this the right way to understand what they were seeing? And my wow, when I saw this discussed at a conference, I said to myself, this can't possibly be right. And so my answer was that the answer is no. This, whatever they came up with, is not legal in any court of law. Nevertheless, I think there is some truth to the folk theorem. We'll see how this works by the end of the talk. So let me review how the classification of the symmetries in the two Higgs double models, so that you can see what this paper Ferrara et al. Ended up finding. So let's neglect fermions, just consider the bosonic sector of the 2x doublet model. There's a kinetic energy term involving the covariant derivative. There's a potential. Here's the most general renormalizable scalar potential gauge invariant. In the 2x doublet model involves 3 squared mass terms, 7 coupling terms. Some of the couplings are real by hermeticity, and some are potentially complex. These 4 here. And the parameter relations of the scalar potential can be the result of a symmetry that preserves the form of the kinetic energy term. And there are basically 2 classes of symmetries. One is called Higgs flavor symmetries. If you have 2x doublet model, it's like having 2 flavors of scalars, and then you can have some unitary transformation like so. And if the Lagrangian's invariant under that, that's a Higgs flavor symmetry. These generalized CP symmetries are symmetries where naively the simplest one is just ordinary CP, which changes scale fields into their complex conjugates. Remember, these are complex fields, but I can also rotate them in the flavor space as well. And so this is called the generalized CP transformation. And all the possible symmetries of these classes have been classified. And for each one, you can ask the question, what parameter relations do you get when you impose those symmetries? And by the way, there can be different symmetries that give you the same parameter relations, partly because we have a renormalizable scale potential, so we're only going up to quartic. If one were to play a game where you did some effective field theory and you allowed dimension 6, etc., then this classification would have to be modified. But in any case, we're not going to distinguish between different symmetries that yield the same parameter relations. Yeah.
Why can't you combine the two and say send phi A to SAB phi B plus XAB phi B star, where S dot vanishes? Wouldn't screw up the kinetic.
Yeah, you have to make sure that the kinetic that it's gauge. You don't screw up gauge invariance kinetic energy.
I think it's okay as long as S dot X vanishes.
All right, let's talk about that at the end. At the end of the day, I can assure you that the all possible symmetries is the list that I'm about to give you here. So maybe there's something of that form, but in some sense, it doesn't give you anything there. So for the Higgs flavor symmetries, here are three possibilities. This is a familiar one, Z2, which changes the sign of one scale and not the other. This U1 is the famous U1 Peche-Quinn. This is a slightly larger symmetry. It's basically the full U2 symmetry that preserves the kinetic energy term, except U1 hypercharges is automatically symmetry. It doesn't change anything because it's a gauge invariant Lagrangian. So I mod out the U1 one. And for the general ICP symmetries, here are the three different classes. And of GCP3, any theta that's not 0.5 pi will give you the same parameter relations. And so now you stick these in the Lagrangian, you ask yourself what relations you get, and here's the list of, this one sets M11 squared equal to M22 squared. This GCP3 sets lambda 6, lambda 7, lambda 4, the imaginary part of lambda 5 equal to 0, et cetera, et cetera, et cetera. There's the list. And you can ask, what about other symmetries that don't seem to be equivalent to the ones I just showed you? Here's one I call pi2, which just interchanges phi1 and phi2. Here's another one which does something similar. Here's something called GCP1 prime, which interchanges phi1 with the complex conjugate of the other. And you can list a whole bunch of these other types of symmetries, and it looks like you get different parameter relations. So are these in the classification? Should this be added to the list? And the answer is no, because by a change of the scalar field basis, you can show that these symmetries just are equivalent to one of the six in another basis, another scalar field basis. So it's nothing new. And here's one thing that always amazed me. This GCP1 prime is equivalent to GCP1 in another basis, even though if you look at GCP1 is just ordinary CP. Phi goes to phi star. It means all the parameters are real. And yet GCP1 prime, if you look at here, lambda 6 and lambda 7 can be complex. There's no restriction of M12 squared, which is a complex parameter, lambda 5, which is a complex parameter. And yet you change the basis and suddenly the corresponding parameters are all real. So that one surprised me when I discovered that. But okay. Now, I can take those relations of the parameters that I showed you on the table, and let's just, here's a list of the one loop renormalization group equations for all the parameters, and you can just plug it in. It's real simple. At one loop, you can do it with a piece of paper and show that those parameter relations are fixed points of the one loop RGD. They're also fixed points to any loop order. So let me do two examples explicitly. So here was a parameter relation which came from GCP2. It sets M11 squared equal to M22 squared, M12 squared equals 0, lambda 1 equal lambda 2, lambda 6 equal minus lambda 7. And now here are the beta functions, and when I write the beta function of M11 squared minus M22 squared, that's the thing that's 0 with this parameter relation. That's equivalent to the difference of these two beta functions. And when you impose the symmetry conditions on this difference using those equations I just showed you, you get 0 in all the four cases. So this is one way of seeing that the parameter relations, at least at one loop, are all stable. And it doesn't take much pencil work to verify this. That RG stability is guaranteed by the GCP2 symmetry. And in fact, it persists when gauge interactions are included. Then, here I've just written the contributions of the scalar potential. They're in the full 2HDM, there are gauge contributions, there are countercoupling. So you can put them all in and check that that these relations don't change. And moreover, the RG stability is guaranteed for all orders of perturbation theory because of the symmetry. Okay, here's the example from that paper by Ferrara et al., the weird one. Here was the symmetry they found. So it again has lambda 1 equal lambda 2, lambda 6 equals minus lambda 7. That's just like here. But instead of this, they just said m11 squared equal to minus m22 squared. No constraint on m12 squared. And yet when you do this calculation, you get 0 at one loop. And then they did it at 2 loops and they got 0. And then they did it at 3 loops, they got 0. And again, with the exception of the Yukawa contributions, which are only verified up to 2 loops, this looked completely renormalization group stable. And the question is why? So now, interestingly enough, if this can be considered as a softly broken GCP2 symmetry, because these two conditions were the conditions of GCP2. And if I softly break it, I could put any mass terms I want. So that actually explains these two lines here. So they're still enforced to all orders in perturbation by symmetry. What is the puzzling one is this one here, m11 squared plus m22 squared. That's parameter stable. There's no symmetry understanding for that at all. So the question was a possible symmetry overlooked? And so this is what those authors came up with. And it was renamed by one of the authors, Ferrara, Goofy, because if you reorder the authors of that paper, you get a nice acronym. So that's where that comes from. So what they said is, let's consider the following scalar field transformations. Here it is. I saw this and I said, come on now, give me a break. Phi 1 star does not transform into the complex conjugate of the transform phi 1. How is this a meaningful transformation? But let's put that aside for the minute. If this is true, then you see the phi 1 dagger phi 1 gets transformed into the negative phi 2 dagger phi 2 and vice versa. Whereas phi 1 dagger phi 2 and phi 2 dagger phi 1 are invariant. So you impose the goofy transformations, and sure enough, you get that parameter relation. So they said, aha, this must be the symmetry, even though I don't think it's a valid symmetry. However, unfortunately, the kinetic energy term changes sign, which is not a good idea, because that means it explicitly breaks the symmetry. So then the authors got extremely weird, and they said, we'll just include in this goofy symmetry changing the space-time coordinate into I times itself, and thereby also the covariant derivative into I times itself. So that means changing gauge boson fields by negative things. And then everything works. But my personal conclusion after seeing this presentation of this work was that this is not legitimate. This cannot be a valid explanation for the RG stability of that.
What's the reason it can't be?
Well, there were two reasons. First of all, I think this is too weird for me.
Oh,
But the other thing is, I don't believe.
Weirdness is not a disqualification.
No, but these, I don't know what. This to me is not a legitimate transformation to have complex fields behaving this way, and I can show you.
It's not familiar, but I don't see obviously why it's.
Because phi 1 star is both phi 2 and minus phi 2.
Yeah, basically.
So pick your choice, right?
Yeah, but there's,
Okay, thank you.
now, I'll show you later, there's another way of understanding why this doesn't really seem to be meaningful, but
Okay.
I can't remember where I have that, maybe later on in the talk. Yeah.
I'm sort of on the same page with you that the symmetry that they wrote down doesn't really seem to make any sense. Is it is there anything to be learned from this work? Like the fact that they still found a transformation that produces the right, like, parameter relationship? Is there anything we can learn from that?
Well, hopefully by the end of the talk, we may have an answer, a partial answer to that. Okay, ask me again at the end.
Yeah, can I have a comment?
Yeah,
So it is understood in cases where you have a symmetry that act on composite operator in a way,
yeah,
does not imply that acting on the, the elementary fields in the way that you expect, ascending elementary field to elementary field. It could happen, for example, in two-dimensional similar model with scalar field theories, like the quadratic term for the scalar could flip sign, but how it acts on the scalar itself is actually not changing the scalar to another scalar, but to a scalar attached to some branch cut. That's
okay,
what potentially resolves the contradiction between the first line that looks totally.
okay, that's an interesting point. Still, you have to understand the kinetic energy terms or.
So in that case, it's understood the kinetic energy is completely kosher because the branch cut cancel one another because you have two operators that appear. So I can explain you in more detail what happens in 2 dimension. I
Okay,
do not immediately see how it works out in 4 dimension,
Oh.
but it's realm of generalized symmetries.
okay, yeah, that's cool. And there's one word I'll say at the very end of the talk, which may.
In 2
relate to
dimension
this.
is the famous Kramer's one duality.
Yeah. I did have some, when I was at the KITP in January, I had some discussions with some people who were sort of mentioning some two-dimensional models that might shed light on that, but they couldn't figure out how to extend it to
Yes,
four
yes.
Okay, in order to try to understand that, I wanted a simpler arena to play with, other than the full 2x double model, because there are lots of degrees of freedom. And what was amazing is that this toy model with one complex scalar field shows exactly the same behavior. So here's the model. Here's a theory of one complex scalar field phi. Here's the Lagrangian. I've imposed a discrete symmetry to remove linear and cubic terms. And now I'm going to impose this relation, m1 squared, that one, and lambda 3, this one, equal to 0. And I do a calculation and I show that these relations are renormalization group stable. Not only one loop, but actually to as many loops as I can calculate. Now here what's the let me try to write a symmetry that might do this. If you do phi to I phi, which is a fine symmetry, that sets m2 squared equal lambda 3 equals 0, not m1 squared. So it explains why lambda 3 equals 0 is RG stable, because this symmetry would be softly broken in the other case. But why is m1 squared equals 0 stable? And so now I can play the same game, invent this goofy like symmetry, phi goes to phi and phi star goes to minus phi star, and end up with m1 squared equals lambda 3 equals 0. But once again, this flips the sign of the kinetic energy term. So it's the exact same structure as we had for the 2x double model. So in my mind, again, there seems to be no legitimate symmetry explanation for the RG stability of m1 squared equals 0.
Did they have any explanation of what this, x mu goes to I x mu meant?
Not really. Not really.
It just seems to be totally.
That was their fix to try to change the sign of the kinetic energy term.
Yeah, you can fix it, but what does it need?
This is why I was very skeptical.
I can see that.
Okay, now to show sort of to get the same sort of results in a slightly different way, I'm going to introduce this terminology, realification of a complex scalar field theory. This is a very fancy term, which is very simple, which is just take the complex field and write it as phi1 plus I phi2, where phi1 and phi2 are real fields. So in this language, realification doesn't change the theory at all. It's just rewriting it in terms of different variables. And so in terms of the real fields, it looks like this. And there are 3 parameter relations, and here they are. these are the parameter relations that are equivalent to m1 squared equal lambda 3 equals 0. And the reason I've done this is because if you look at these parameter relations, they look exactly like those two HDM parameter relations. Lambda 1 equals lambda 2, lambda 6 is minus lambda 7, and m2 squared is minus m1 1 squared. So now we're getting something that look very similar to in a much simpler setting. And so now we can ask the question, well, again, these two parameters, now you can calculate the RGEs in the realified theory. Of course, you get exactly the same answers as we had before. And again, these parameter relations are due to the fact that they're a consequence of a softly broken symmetry, but this relation has no symmetry explanation so far here. Now, what would be the corresponding goofy-like symmetries to enforce that parameter relation? And the answer is this: phi1 goes to I phi2, phi2 goes to minus I phi1. But remember, phi1 and phi2 are real fields. So to me, it is not meaningful to talk about a symmetry of real fields and throw in complex numbers. But nevertheless, RG stable to all is progression. Some technical details going beyond one loop here. Here are the two loop formulas I've written here that we've used. They're sitting in the literature. There are even three loop formulas sitting in the literature, and can check everything works as I said. Now, one thing that will be of interest to us a little later on is when you find that, say, the two loop beta functions are 0, when you impose the symmetry conditions on the parameters. Notice that this guy here is the sum of two different type terms. These are linearly independent tensor structures. And so when you find that this is equal to 0, what you also find is that this guy is separately 0, this guy is separately 0. And same here. This guy is separately 0, and that guy is separately 0. So as you go up in order of perturbation theory, when a beta function is equal to 0, it's a much stronger constraint. There are lots of linearly independent pieces that make up that 0, and each one of them has to be 0 separately. And we did check that that's exactly what happens. So that will be useful to us later on. How did I attempt to explain these parameter relations? And I noticed that this illegitimate symmetry would have been legitimate if the phi I were complex fields. So our proposal was to promote these two real scalar fields to complex fields and then impose now legitimate symmetry transformations like so. And I'll also impose a CP symmetry that imposes reality conditions on the scalar potential parameters. So then the resulting parameter relations of the complexified theory. Now, the complexified theory is not equivalent to the original theory. It has twice the number of degrees of freedom. But any resulting parameter relations you get from now this legitimate symmetry will be RG stable. And so what I'm going to show in the rest of the talk is that the corresponding vanishing of the beta functions of the complexified theory are going to eventually imply that the beta functions of the original real theory are also 0. That was the idea, and it takes a little work to get there, but that's going to, in some sense, restore the Folk theorem by saying, I have a parameter relation. Yes, its origin is a symmetry, but it turns out to be a symmetry of an extended theory, not the original one. So the complexification recipe is start with a real scalar field theory, promote each scalar field, real scalar field, to a complex field, define the complexified model now by just replacing the original kinetic energy terms with a standard canonically normalized kinetic energy term. I'll impose appropriate Z2 symmetries to eliminate odd numbers of fields, promote the goofy-like symmetries of the real scalar field to legitimate symmetries of the complexified theory, impose CP so that scalar potential parameters are real.
And I assume you're not gonna let X go to minus.
No.
Back to X.
No.
That's good.
The thing is, once I've promoted these to legitimate symmetries, the kinetic energy term doesn't change sign.
Yes.
And sorry, the potential, is it real or is because now it would be a complex number since now it becomes a.
Yes, so I'll show you exactly what the new scalar potential is. Now, here I'm going to introduce a notation that I find very useful, if nothing else for typographical reasons, where this kinetic energy term is invariant under, well, and this A goes from 1 to 2. It's invariant under a U2 basis transformation like so. And what you see is I'm going to put bars on the complex field, on the complex conjugated fields. And then I'm going to establish a rule where I only get to sum barred and unbarred index pairs. That's going to be the rule. And by establishing this notation, in some sense, everything is expressed covariantly in this language. And it's very easy to keep track of what's going on. Now,
Why determinant equal to 1? I mean, it's not necessary. It's not
why did I write the term? It's not necessary. You're right. Yeah, I don't need that actually. I don't know why I wrote that. Yeah. No, please ignore that. Yeah, so now I should say that in the literature, there's a slightly more common notation where instead of unbarred and barred indices, I do lower indices and upper indices. That the complex fields have upper index, and it's equivalent. And the only reason I do it this way is because it's sort of easier to keep track of the order of the indices that appear in a given tensor. When some are upper and some are lower, you know, you have to have all these extra spaces, and sometimes it's easy to make an error. And so what's going to be amazing about the analysis that comes out is that the analysis almost falls out of the notation. Once I get to understand the notation, the rest of it almost happens by itself. And so let's see how this goes. So here's the scalar potential of the complexified theory. And again, I've gotten rid of terms that are odd numbers of fields. And so this is the most general normalizable scalar potential with an even number of fields. And I've been careful to put bars on the appropriate things. And so here, for instance, I sum over A bar, and B bar, et cetera, et cetera. And the only thing you have to keep in mind is that, for instance, M squared with 2 unbarred indices, oh, I should have written AB bar. I didn't, sorry about this. M squared AB and M squared AB bar are independent tensors. So in reality, I should have given them different names, but I kept the same letter. So in order to follow things, you have to pay attention to how many barred indices there are and how many unbarred indices there are. Now, hermiticity and permutation symmetry imply some various relations. Here I've written it. So for instance, if I take M squared AB and I take the star of it, I get M squared A bar B bar. So that means that this term is really the Hermitian conjugate. What the hell happened here? Sorry. No, this is okay. this term here is the Hermitian conjugate of that term there, for instance. Okay, so you can write out all the relations that are relevant based on these properties here. And then you can quickly see that some of these parameters are real, others are complex, etc. Okay, so now remember, I have a symmetry that was the illegitimate symmetry in the case of the original model, but is a legitimate symmetry in the complexified model. It was this, and now I can ask myself, what does this impose on those parameters beyond these relations here? There are extra parameter relations, which are now imposed by the symmetry. And I've written them all out completely. Here they are. So you don't have to follow in detail every one of these, but again, it's a straightforward calculation. And then I impose HEP symmetry, which means that every complex parameter is now real. So in fact, I take a, say, M11 squared, it would be equal to M 1 bar 1 bar. So fewer parameters at the end of the day. You could ask how many are left. The answer is that there are 3 independent squared mass parameters and 11 independent coupling parameters. And so of the 11, for instance, 4 of them appear in this lambda with 2 1 bars and 2 bars. 3 of them appear where there are no bars or all bars, and then 4 of them appear when there are 3 bars, 1 bar, and vice versa. And again, these are independent tensors. You can really see it from here that if you have various relations, and then things that involve this one will have to separately vanish compared to things that involve that one, because they involve completely different parameters. Okay, now I should tell you what motivated me to this language of realification and complexification. And I was amused by the, realification and complexification in mathematics really starts out with studying vector spaces. But as far as physicists go, they really see this often in Lie algebra theory. And just to give you an example, if I take the Lie algebra group SL2C, which is the set of complex traceless 2x2 matrices, I can first realify it. What does that mean? An element of SL2C is a complex linear combination of those 3 generators, but I can just as well write it as the real linear combination of these 6 generators. That doesn't change the nature of the group, the algebra. It's the same algebra, but I give it a notation, SL2CR, because it has 6 generators. And by the way, that's the thing that is isomorphic to the Lie algebra of the Lorentz group. Lie algebra of the Lorentz group. And it's one of the bones I pick with many of the books that basically write this isomorphism and don't let you know. They say that this is what's isomorphic to that. And if for a mathematician, which I'm not, but this is a complex Lie algebra, that's a real Lie algebra, so it doesn't make sense to be equating those two. What you're really doing is equating those two. But now I could complexify this by now allowing complex linear combinations. And when you do that, you actually get a direct sum of 2 copies of the original complex Lie algebra, which, by the way, is isomorphic to that complex Lie algebra. So this is the analogy of what we did. We started out with a theory of 1 complex field, we realified it, and we now have 2 real scalar fields, and then we complexified it, and we have 2 complex fields. These 2 theories were exactly the same written in terms of different variables, just like these 2 were basically the same object written in a different way. Whereas this is a different object than that, in the same way this is a different object. So that's where this came from. Okay, so now let's look at the beta functions of the complexified theory. Now, one way to work out the beta functions is now to take that complexified theory and realify it again, and then I'd have a theory of 4 real scale fields. Then I can use all the formulae in the literature. But that's a lot of work. Actually, we did it, but in any case, what I thought was more useful is to write those beta functions directly in terms of the complex parameters. And so I worked them out. So here they are. And what's kind of nice about this, these coefficients here require a fair bit of work. And it turns out I don't care about those coefficients. They will turn out to be completely irrelevant. Because when this thing is equal to 0 after imposing the constraints, each one of these terms is separately going to be 0 because they're linearly independent. And that was an important observation in going forward. So, for instance, if we have a parameter relation, m11 squared equals minus m22 squared, which let me write it like this, and then these coefficients are kind of trivial here. What the symmetry guarantees, because I'm in the complexified theory, the symmetry is valid. The symmetry guarantees that this equation, when I impose the parameter relation, I get 0. That means they're RG stable. And as I said, each one of these, this looks like one equation, but it's 3 equations. Each one of these is separately 0. So I've
When
written
you
that.
say parameter relations, it's not the general complexified theory, but the specific one that you got when you started with a smaller theory. So
No, it's the parameter relations in the complexified theory. Here, I wrote them here. If these these are the parameter relations.
when you have already imposed the symmetry that you were inspired to do.
Exactly.
Because of, and not the general one, so it's
Not-
not a general description of that theory. It's a sort of.
Yeah, this is a specific symmetry that I've imposed.
Symmetry, it's sort of.
Yeah, it's a specific symmetry, but once I've imposed it, I derive those.
I understand.
Those are the things I'm putting on the right-hand side of those beta function equations when I evaluate them. And so, as I said, when I do that, each one of these terms is separately 0. So here I've written the 3 equations. And now if I look at this second one, and if you look carefully, now remember, because the these parameters are all real now, because I've imposed reality on the parameters by CP, this equation looks exactly like the beta function equation of the original real theory. And so I basically, this so far is just one loop, but in one loop, I've now explained this vanishing of the beta function in terms of the vanishing of one of the pieces of the beta function in the complexified theory. And so the question is, does this work to all orders in perturbation theory? So let's just look at what happens at 2 loops. So 2 loops, I'd written out this beta function here. And now I told you that there are 2 separate tensor structures here. So in fact, this beta function equals 0 is really 2 separate equations. And now what I want to do is I want to ask the question, are these equations being satisfied due to the complexified theory? So the corresponding equations for beta 2 for m squared with either 2 bars or 1 bar, these are much more complicated. Remember, 1 loop, it looked like this. The 2 loop versions of this written in terms of the parameters of the complexified theory, lots of terms. But the point is that if you look at this structure, now I can use covariance, and I can tell you what types of terms could appear on the right-hand side. That's the beauty of this barred, unbarred notation. It basically sort of leads you to the structure on the right-hand side. And again, I don't need the coefficients because each term is going to be linearly independent and must separately vanish. So I can ask myself, wait, what? let's see. So I can ask myself, what sort of equations will I get in the complexified theory? And these are two of the equations among many that I will get. They look like this. And there are others, but in the same way that over here I had 3 equations, at tulips I'm going to have lots more equations. But all I need to do is focus on a few of them. And in particular, I'll focus on these. And again, it was just tying up barred and unbarred indices in all possible ways tells you what the structure is going to be. And now I have to impose the conditions on the parameters, and I've rewritten them here. These are the relevant conditions on the lambda parameters by the symmetry. And these equations almost look like these. The only difference is that if you look here, in this equation, one of the lambdas has 2 unbarred and 2 barred. See, at one loop, everything either was all barred or all unbarred, and they were the same, of course, of the reality. But here, it's not, I can't quite do what I did before. However, this equation must hold for all possible choices of lambda with 2 unbarred and 2 barred, numerically. And so I can choose whatever I want. And the point being is that the only condition is that these symmetry conditions are cold, but these match exactly. This one just says that this one's real, but that's fine. These things match up one against the other. So because of that, I can actually, even though lambda A, B, so lambda A, B, C, D, there turn out to be 4 independent choices. If you allow A and B go from 1 to 2 and put the symmetry conditions, there are 4 possible independent things there. Here, there are 5 independent things. However, of the 5th independent thing, I could just set to the 4th independent thing and just match them up. And so, since this is true for any choice of these lambdas, it must be true if I make this specific choice. Namely, I set that guy equal to that guy. Yeah.
Sorry, just to take a step back
Yeah.
for a second. It is clear to me that you've shown that these beta functions are 0, and it's clear to me that you've shown that they're equivalent to the beta functions in the non-complexified
Right.
theory. Maybe this is a naive question, but it's not obvious to me that these beta functions are 0 in the complexified theory only because of some other property of the complexified theory. Like the mapping back to the non-complexified theory is not obvious to me.
Oh, I don't have to map it back. Once I get these 2 equations to be equal to 0, they're equal to 0 because of the symmetry of the complexified theory.
Right?
But now once I have these equations, I compare them with the corresponding equations in the real theory, and algebraically they are exactly the same.
I guess
Everything's the same about what goes into here and goes. What goes
Okay.
into here, when I say sim, I mean I impose these conditions, namely this, but the equivalent conditions hold
in the non-complexified
in the
theory.
non-complexified
Okay.
theory as well. So algebraically, the equations just match up exactly. The only non-trivial statement was the realization that I can just numerically set that like this. And I can do that because they're linearly independent, and they must be true even if I don't set it equal to that. So that means I can set it equal to it. And this sort of argument just goes any order perturbation theory, because at the end of the day, the key point is I can always find a set of equations that just involve an even number of barred and unbarred indices. Had there been an equation with 1 bar and 3 unbarred, I couldn't make this argument because because the additional constraints on the lambda with 3 bars and 1 unbars don't have this structure. So I wouldn't be able to do a similar argument to match up the equations. But the fact is, it's just by, again, the notation gives you the proof in some sense. That when you write down the most general beta function, there will always be one of the independent tensors that appears in the list will be one with just an even number of bars and unbars. Okay. So in some sense, let me summarize the argument. Schematically, we have the beta function given by something like this. And whatever this FK, it's the sum of lots of different independent things. But the one thing you know is however you combine the various tensors, the number of free indices at the end of the day must be A bar, B bar to match it on this side. And so all you need is to find some value of K where you get an equation here like this, which matches exactly the original beta functions of the beta function of the original theory. And so that's really the origin of the result. The RG stability of the parameter relations, the original scalar theory, are inherited from the symmetry of the corresponding complexified theory.
Howie,
Yeah.
so you said the coefficients don't matter because each term is linearly inherited, but what if the coefficient were 0? Then you don't get a constraint.
Yeah, if
It could be a 17 loop order or something.
yeah, so it depends on that thought did cross my mind. But at least, so all I could say is I've looked at the expressions for the beta functions to some number of loops in the literature. It's gone at least 3. I've looked at 3. I think there are even some at 4. And basically any tensor structure that can appear appears. But you're right in the sense that if you were really wanted to make a formal mathematical proof with no loopholes, there's always that loophole lurking behind, as you say, 17 loops. By accident is a 0, one of those coefficients. But so I don't know what to say other than that I would say this is very strong evidence for what's going on. And that's as good as I could do for the moment. So let me just mention, finish off by mentioning some future directions. One thing is this gives me a recipe for finding other examples that lead to similar phenomenon. So start with a theory of n complex scalars with some RG stable parameter relations due to some Higgs flavor symmetry. Now, if I had n of them, then this would be some subgroup of UN, the symmetry group of the kinetic energy terms. Let me impose CP to ensure reality of all scale potential parameters. Take that theory and now retain only terms of the scale of potential that are holomorphic in the complex fields. And that just means phi A and not phi A bar. Okay, so I'm taking the original theory, I'm just picking out a subset of terms. Here they are. So now I'm sort of reverse engineering the process I just showed you in this talk. And then construct the following theory of n real scalar fields with the recipe, replace the phi A with n real scalar fields, little phi A, replace the kinetic energy term with a canonically normalized kinetic energy term for the real scalar fields. And by the way, that maximal symmetry group is ON. And if the Higgs flavor symmetries of the complex scalar field cannot be embedded in ON, then that Higgs flavor symmetry will not survive as a legitimate symmetry of the real scalar theory. And that's exactly, if you go backwards now, take the complexified model I had with that symmetry, phi1 goes to I phi2, phi2 goes to minus I phi1. That matrix, 0I minus I0, cannot be embedded in O2. And that's one way of thinking about why there didn't seem to be a legitimate symmetry in the original real scalar field theory. But nevertheless, by the same arguments as I've shown you in this talk, the parameter relations are of the same form in this real scalar field theory constructed in the way I just outlined here. And so you will have another example of a real scalar field theory with parameter relations that are RG stable without a symmetry. So that's one possible direction. The second possible direction is, does this argument, which was constructed for the toy model, is this the explanation for the full 2HDM model that was written by Ferraro? And so what would you have to do? You take that 2x double model, now they're the complex field, so you have to realify it in the same way we did when we started out with one complex field. And so you write phi1 and phi2 like so. Now I have 8 real scalar fields. Now the goofy symmetries now look like this. And again, this is another reason I couldn't buy their explanation. Again, I don't think it's a legitimate symmetry to have a theory of 8 real scalar fields and impose symmetry transformations with extra i's like that. Okay, so now we have our 2HDM written in terms of 8 real scalar fields. So complexify the theory, promote phi I to 8 complex fields phi A, impose CP symmetry, verify the RG stability of the 2HDM. With that can be explained by the symmetries of the complexified version. Okay, if you ignore the Yukawa couplings and the gauge couplings, this would just be exactly the same sort of exercise that we did in the toy model. But now one should include the gauge fields and the fermion fields. I don't think this will change the picture at all, but it's probably worth a little thought. And the last question is, are there more sophisticated ideas that might provide a deeper understanding to the phenomenon I've been talking about for the last hour? And so when I talked to various friends when I was at a meeting at CERN, the buzzword I heard was outer automorphisms. And then a paper just came out a week and a half ago by Andreas Troutner, who I had many discussions with. He does not complexify things. He attempts to somehow give some sense to that transformation where the complex field doesn't transform as the complex version of the original field. I suspect that what he's done is really secretly complexifying, but I'm not 100% sure. He has a very interesting take on the kinetic energy term. So what he says is that I do a transformation, it changes the sign of the kinetic energy term, but that just means that the kinetic energy term of the quote new Lagrangian is no longer canonical, but I can always then take that guy and recanonicalize it. And so in some sense, that changes things. And my understanding from I haven't understood everything he said in this paper yet, but my understanding is when you do that, you find that this parameter relation the weird one with m1 squared equals minus m2 squared just gets modified, and you're back to one of the original 6 allowed symmetries of the 2 HDM. So maybe there's some interesting things to think about there. Generalized symmetries, when I talked to people at KITP, that was the first thing certain people said to me, and then I said, well, how will this be relevant? And the only thing that they said was, well, generalized symmetries may be a way of understanding in a broader context certain properties of the quantum field theory that are not obvious from studying the original regular symmetries that we all understand quite well. But there was no real concrete proposal yet. So I don't know whether there's some direction in like that might shed light on this. And from what you said also, that was mentioned as a possibility, some phenomenon in 2-dimensional theories that might have relevance here as well. It would be interesting to pursue that. But that's where I'm at now, and thank you for your attention.
Start raising this up to gauge and you countless sectors, things like that. You can have non-perturbative effects beside this beta function things.
Yeah.
Can you incorporate that somehow into this picture, or that's just completely different?
I don't know the answer off the top of my head. Interesting question. Worth thinking about. Yeah, everything here is in the perturbative regime. Well, the perturbative computation. So yeah. Maybe there's something to think about non-perturbatively as well. Yeah.
I was just wondering, so it looks like you have a situation where it looks in the original goofy symmetry transformation, it looks as if it would be the symmetry, but it maps degrees of freedom that aren't independent in a way that's inconsistent. And then your resolution is you sort of upgrade this by just adding more degrees of freedom,
right,
so that these symmetry transformations are valid.
Right.
But when you say it like the way I did, it doesn't seem anything specific to complex numbers and real numbers. So I was wondering if you had any ideas about like a situation where you have a similar sort of idea, but it's not complex and real numbers.
Yeah. I haven't thought of any way, any example of that. So the answer is I don't know. I mean, the reason why I thought about complexification was precisely because this is what inspired me to think about complexification.
Yeah.
When I rewrote, well, actually, this was written in the original paper for et al. Where they noticed that in terms of the real fields, the transformation was like that. And to me, that was screaming out for complexifying the model to make some sense. But are there other examples where there may be some extended real theory, for instance, which you can play the same game? I mean, in some sense, if I go back to my simple example, so here's my complexified theory. I can realify this theory now, and I think I mentioned that briefly, where now I have a theory of 4 real scalar fields. So in some sense, I have extended the original theory of 2 real scalar fields into a theory of 4 real scalar fields. And since that theory of 4 real scalar fields is equivalent to this, so you would get the same answer. But I found that working directly with the complexified theory sort of led me to the proof that that the beta function equations that needed to vanish were algebraically identical to the original theory. It was, at least to me, much clearer when I wrote it using complex field. Yeah.
Well, mine's really off the wall. I may regret asking it. It seems like we would like it if we had a standard model where the Higgs mass didn't run. And, right,
Yeah,
can you, and somehow, but we don't see evidence of two Higgs doublets.
right.
So that's not a immediate solution, but but somehow what you're doing, I think, says that if you can somehow have a theory that looks like it's got, let's say, twice as many fields,
Mm-hmm.
like a two Higgs doublet, but it's really got fewer fields because of some symmetry that you can impose with a theory that seems to have more fields.
Yeah,
And I'm just wondering if you could sort of imagine injecting some constraint on the beta function
okay,
in that sort of backhanded way.
yeah, and someone asked me separately whether one can imagine some solution to the hierarchy problem.
Well, that's what- yeah.
Explained this way.
Yeah, that's.
I don't think so. The hierarchy problem is a question of. It's not really a question of parameter relations per se, it's a question of scales.
Well, that's why I was referring to the beta function.
Yeah, but I can tell you what, here's something. To that. It's not what you're asking, but it's a question that sort of seemed to. Come out. So if you look at this, here's the realified version of the original theory. Notice that the parameter, the square and mass parameters are like that. So this tells you that there's going to be spontaneous symmetry breaking. Now, normally, before something like this, I was not aware of a theory where spontaneous symmetry breaking was being mandated by a symmetry. But it seems to happen here. Unfortunately, in the context of the two Higgs doublet model, when I start to add the gauge bosons and the fermions, it wasn't clear that this was going to be preserved. But in any case, it was an idea trying to think of. Let me explain why I say this. When you bring in the specific challenge of the fermions is to find symmetry transformations of the fermions that go along with the symmetry transformations of the bosons to make it symmetric. And so, for instance, that GCP2 symmetry I showed you before of the two doublet model, turns out when you try to extend that GCP2 symmetry to the fermions, you get something which is not phenomenologically viable, because you don't get the right CKM matrix, et cetera, et cetera. So if we didn't have fermions in the world, this would be a very nice way of explaining why you have symmetry breaking in this particular scalar sector. So whether there's some model building you can do to somehow make the fermions preserve this, I would find that very interesting.
Well, and finding M1 squared is 0 is not something that's usually easy for a scalar field, isn't that right?
Well, yeah, I mean,
somehow there's some secret.
well, here, I mean, in the original theory, one complex field. Oh, no, this is fine. Right. Yeah, so it was easy to find the symmetry where M2 is equal to 0.
But we can't do that in the standard model.
Yeah, well,
And so I'm just thinking,
yes,
if you
right.
could somehow embed the standard model in
Yeah.
that, you might get a way so it's another way of asking the first question,
Right.
which is somehow explain the hierarchy.
yeah. All worth thinking about. I don't have an immediate answer to that.
And
Are there other examples of RG stability without a known symmetry?
I didn't know of any before, so that's why this was a surprise to me. At least in four-dimensional theories.
To a certain order, there are examples, but not to the orders that was pretended in there. There's certain miracles.
You mean it's known that it doesn't work at
So there are
higher
examples
order, it
where,
just hasn't been shown.
there are examples where you expect the coupling to run, but it doesn't run to a certain order, but then start running later.
Okay,
Oh, I
that's,
see.
yeah, it's not just that they only checked it to that
Yeah,
order,
yeah.
they know it.
Yeah.
Oh,
Sort of-
oh, that's
It's running
interesting.
is postponed.
Yeah.
But that could be nice for the Higgs theory, that might be enough to explain the hierarchy problem, if you could somehow make it do that.
Hmm.
And in those models, there was also a trick by coupling the model to additional sector. And then somehow argue the other sector is, only contributing to a higher order, but not to the lowest orders.
We should think, Howie again, if you have a question.
I found around for the rest of the week.
I have a grandson and his family visiting. So I may be flying low.
Well,
for the week.
I mean, no.
Yeah.
I guess
And in
I wanna
fact,
ask
it's
you something,
necessary.
right? So like.
Arlo
like a
is
Compton experiment, right?
accessory,
Let's say,
so
I
it's
just
like-
take the
Yeah.
model, or even just the original uncomplexified
But it's Will.
starting theory, right?
Yeah, Will and
And I
his kid and his wife.
Do,
They're,
LHC, I do some sort of collider measurement, I see
So then they'll be.
X amount of, degrees
Similar
of
regards.
scalars, right?
Okay.
Yeah, I actually-
And they satisfy this relationship, the.
Yeah,
this-
Will and I were
this
talking
kind of those, or which is what was observed from the big
about a
functions.
potential project, but it's been so
But
busy.
it seems like when you complexify, you have twice as many
Oh, I
scalar
thought- are
degrees
you
of freedom,
gonna
twice as
do
many
that?
scalar fields.
I'll be at
Mhm.
Flatiron
But
tomorrow. and-
I should be able to see
I'll be at
those
Flatiron
twice as
tomorrow,
many
actually.
But you'll
scalar
be in
fields,
New
right?
York
in-
Yeah, I'll be
tomorrow,
there.
Cause I know. there's
Friday,
some-
right?
Friday,
They're
I'm actually going
extremely
to
happy,
upstate New York.
right?
I'll be in New York.
How do I-
Part-
Oh,
How do I go from,
Just to have a-
I haven't been.
No,
to
I
my
would-
club since New Year, so.
I would say that
Where are they?
the complexified theory is not supposed to be something physical, it's just it's a mathematical.
Oh, gee.
right, but what's confuses me is like, why, like, if nature, they're two sandbox, they're two different theories.
I mean, suppose, yes, they are different theories,
Yeah.
so
If you feel like
suppose
talking.
we discovered the second mixed double.
I'm always-
Forget your.
Then M1 squared was minus M2
What
squared.
he's doing is.
I don't think that would
Yeah, he's
imply
not
that they're
flashing.
void.
Yeah, we were thinking about.
Right, but that's,
yeah,
but
this
that's,
Wakehorse paper.
I'm so confused about is that if you can
And so we were chatting.
explain this behavior just within the original theory,
Right.
it's like, why this? It seems like the answer to this must be within that original theory, like.
Well, that was Troutner's attempt to do
Yeah.
that, is to explain it within the original theory.
Right,
As I said, there's one step in what he does that leads me to believe that secretly there's a
Right.
complexification going on, which he's not telling you about, but maybe not. So that's an interesting avenue to pursue.
Yeah.
I would really like to understand this paper a little better to see. And the folks who suggested to me, well, what about generalized symmetries? That would be their point. of
right,
view.
right, within.
If there
the
was
same framework,
within
yeah,
that
yeah.
framework, but slightly expanding your notion of a symmetry, maybe there's some way of discussing it. So I've used the complexification as a crutch, really. And at the end of the day, we may not need that crutch, but
That paper was very recent, it looked like it was 2025, is
The-
what,
the Andreas,
I think that was his name, something Lautner, what was his name? Or
Troutner.
Troutner, okay,
it came out April 30th.
That's very recent.
Yes, very recent. But I was talking to him about this in October at CERN, so I knew this